we will be solving the time-independent Schrödinger equation for a shifted direct delta potential, which is our v of x is equal to v naught plus alpha times the direct delta function. Now we will start off by breaking them up into regions. We will have 4 regions. We will have region 1, which will be having transmitted and reflected waves for below v naught, and then above v naught we only have our transmitted wave. As for region 2, it will have a in this case there will be inside the barrier, so it will be transmitted and reflected, so C and D, and then above v naught it will be transmitted and reflected for C prime and D prime, and then for between 0 and A, well x is between 0 and A, it will also be inside the barrier, reflected and transmitted waves, so E and F, and then above v naught it will be E prime, and then for region 4, which is x greater than A, there will be a transmitted wave of G, and then a transmitted wave for G prime above v naught. Now, we will simply start off by solving the time-independent Schrödinger equation for E below v naught for region 1, region 2, region 3, and region 4. Now, region 1 and region 2, and region 3 and region 4, they're all similar in some way, but in region 1, in the case, it will start off with negative h bar squared over 2m d squared dx squared plus your potential psi equal to E psi, right? Now, from what we learned in previous classes and just overall, that you would, in order to solve for it, you would have to just divide your negative h bar squared over 2m by the other side, which will leave you with d squared psi dx squared. And in region 1, there is no potential, so this goes away. I should have stated that earlier, my apologies. But you will just be left with 2m e h bar squared negative, right? So we can simply just use this as a constant k. So this goes to d squared psi dx squared equal to k psi. Now, from here we know that the general solution for anything that looks like this will be in terms of exponential. So the psi of 1 of x is equal to ae ikx plus be negative ikx. Now for region 2, we do have a potential, since it's between x is between from negative a and 0. That potential will be v naught. So then for region 2, it will be negative h bar squared over 2m d squared psi dx squared plus v naught equal to E psi. Now in this case, since we do have a potential, we will be subtracting v naught onto the other side and doing the same process once again, but this will leave us with d squared psi dx squared equal to 2m times E minus v naught over h bar squared. Yep. And then similar, once again, we can rewrite this as a constant k or k2 psi. And instead of there being i's, it will be considered like a real solution. So psi of 2 of x will just be CE kx plus DE negative kx. Now for region 3, it will be similar to region 2, and it will apply the same cases, just with different coefficients. And so then it will be psi of 3 of x is equal to E kx plus f E negative kx. As for region 4, it will be similar to region 1, where it will, the solution would be psi 4 of x equal to g e I k x plus h e negative I k x. But since there's no deflection, h goes to 0, leaving us with psi 4 of x equal to g e I k x. For x greater than a. So this is for x greater than a. Region 3 is for x between 0 and a. Region 2 is for x between negative a and 0. And region 1 is for x less than a. This will now leave us with 7 equations and 6 unknowns. Now, in order to solve for those, we will be applying our boundary conditions, and our boundary conditions will be for x equals to negative a, and x equals 0, now, so solving for our boundary conditions, it would be psi of 1 equals psi of 2, so it would be your psi of 1 equals psi of 2, which where we will be psi of 1 negative a equal to psi 2 negative a. So then plugging those boundary conditions in, we will be left with the AE IKA, well, negative IKA plus BE IKA equals CE KA plus DE KA. Now we just have to find the derivative of that. So we have solved for our derivative for the psi 1 equal to psi of 2. Now we will be validating the boundary condition for x equal to 0, or where the direct delta has a discontinuity. So we will just be applying our Schrodinger equation for with our potential for V naught plus alpha times the direct delta function, psi equal to e psi. And in order to just solve for that, we will be breaking them into integrals. So here in this case, we will just have our tangent equation divided into an integral with our potential that we had already found, but then we know that e minus v naught is a constant, so then that automatically goes to 0, leaving us with the just these constant, which we take out of the integral, and then just our d squared side dx squared, and then alpha also goes outside the integral since it's a constant, and then just leaving us with our direct function. And from there, solving for that, we will just end up with negative h bar squared over 2m d side dx on the interval, or the 0 plus or minus, equal to 2m alpha over h bar squared psi 0. Well, in this case, we just divide that from what our alpha that we originally have here. So this would just be gone, and then our solution, or just continuing for derivative, would be that. And so now we also apply another where psi of 2 is equal to psi of 3, psi of 2 equals to psi of 3, psi of 2 equals to psi of 3. And when you are applying for that, you just have your zeros in each x. So then that would only leave us with the psi of 2 of 0 minus psi of 3 0 plus. So then that would just leave us with c plus d e plus f. Since anything times 0 and anything e to the 0 would be 1, where the derivative is not continuous. Now when we apply it for our other boundary condition where x is equal to a, where x is equal to a, that will be your psi of 3 equal to your psi of 4. So now you would just be, once again, just psi of 3 equals psi of 4. And then just taking the derivative of that. So here we will be having our boundary condition for x equal to a. You will be substituting psi 3 equals psi 4. You derive that, and then you will just end up with the derivation of your original equation. Now I will just be writing down the applying the a is equal to 1 for normalization, which will just be our way of helping to solve for these equations and these unknowns.